Mr. P helps with the algebra here, and we are going to be doing Unit 4, Unit 4, Topic 1. This is lesson number 6, which we are, there it is. So tortoise and hare, so we're going to be exploring the differences in the rate of changes of quadratic and exponential functions. That's what we want to do before we're done with this. We're going to start off with a warm-up, which is going to be about determining if it's a function or not. If it's a function, we know that a table or graph or an equation is a function if each domain can only have one range. So I'm going to check this set of coordinates, and what I'm looking for is a repeat in any of the domains. And it looks like I found one. It looks like the domain of 2 has two different ranges, -1 and 5. So this is not a function because of that. And I'm not going to be writing the answers on here. You're just going to have to listen to me and write it and describe what I'm saying yourself. So the number of calories you burn is burned since midnight at any time. So time versus number of calories. There's your two variables. So time is always the independent and number of calories is always the dependent. Well, in this case, it is the dependent. But time is always the independent, pretty much. So I need to ask myself, at any time, is it possible to have burned two different amount of calories? No, that's not possible. So this is a function. No domain could ever have more than one range. So if it's been 5 minutes, you can't have burned 1,000 calories and 2,000 calories at that same time. That does not make sense. This is a function because it passes what we call the vertical line test. There's no place on this function. This is a piecewise. It's two linear pieces. But there's no place on this function where it hits the function twice at the exact same time. I'm looking once again at the table. I'm looking at the x's. I don't see any of them repeating. So that tells me that this is a function. The fact that they all have the same range is meaningless to me. That does not mean anything because that just means that at all four of these different places, they had the same height. So that's like point here, point here, point here, point here. That there's no place there that's going to have 2 points on top of each other. They might be the same height, but that's meaningless. That's still a function. This is not a function because this piecewise, which is made up of 2 angles, I want to say they're hyperbolas, but they're not, clearly. They kind of look like hyperbolas, but they are not functions because I can draw a line right here and it can hit twice and it's not a function. This one is a function because no matter where you put a straight line, it's never going to hit the graph twice at the same time. All right, so moving on to the lesson. So we're exploring rates of change, which was in the last video. But now we're really going to look into, how is quadratics and exponentials, they look very similar. So how are we going to tell them apart? And what we're going to do is we're going to first list, the tortoise, by the way, if you haven't read the directions. So basically the hare is going to be the quadratic equation, t squared or x squared. And the tortoise is going to be represented by the exponential equation of 2 to the x power. So what we're going to do is we're going to come up with a table that shows all of the possibilities and then graph them so we can then look at, where and who is changing their rate the most and when are they the same. We can answer all kinds of questions. So let's pretend 0. 0 squared is 0. 0 times 0. 1 times 1 is 1. 2 times 2 is 4. 3 times 3 is 9. 4 times 4 is 16. 5 times 5 is 25. And 6 times 6 is 36. So that's easy. Now, I'm going to do something really weird here. So actually, over here it's going to be really weird. But over here it's not so weird. So that's plus 1, and that's plus 3. And then it goes to plus 5, and then plus 7, plus 9, plus 11. Now, that makes sense because quadratics have a second difference. This was 7. That's plus 2, plus 2, plus 2, plus 2. Common second difference. Now, exponentials, 2 to the 0th is 1, 2 to the first is 2, 2 to the second is 4, 2 to the third is 2, 4, 8, 2 to the 4th is 16, 2 to the 5th is 32, 2 to the 6th would be 64. Now, we know, and we have explored in the past, that exponential functions have geometric patterns. Times 2, times 2, times 2, times 2, times 2, times 2. I'm going to do something pretty weird right now, which is I'm going to actually list the differences because rate of change has to do with differences. So this is plus 1, and then it goes to plus 2, and then it goes to plus 4, and then it goes to plus 8, and then plus 16, and then plus 32. Now, what you might be noticing here, and we haven't talked about in this in the past, is that this exponential equation has differences that have a geometric pattern. So exponentials have differences, although we like to think of as geometric patterns. Exponential functions have differences that have a geometric pattern also. So not only do the numbers have a geometric pattern, but so do their differences, if you want to look at it that way. All right, so let's graph 0, 0. So I'm going to graph the red for the quadratic. 1, 3. I'm going to assume that each box is worth 1. So 1, 1 would be right there. It is very important that you are doing this precisely. 1, 2, 1, 2, 3, 4. Might have been better if I'd set up the graph in advance. Next one would be 3, 9. 1, 2, 3. 1, 2, 3, 4, 5, 6, 7, 8, 9. The next one's going to be plus 7. So I'm just going to write 1, 2, 3, 4, 5, 6, 7. And then the next one's going to be plus 9. Write 1, 2, 3, 4, 5, 6, 7, 8, 9. And I don't think the last one's going to make it. 36 isn't going to quite make it on the scale. So there's our quadratic. And I am not being as precise as I would really like to because it's kind of hard to write on here. But if you're being really precise, because like I said, these two equations are going to look very similar. 0, 1. So this one started up here. So really the tortoise is getting a head start, because anything to the 0th power is 1. So it looks like after 0 seconds, the tortoise is getting a head start. After 1 second, he's 2 above. After 2 seconds, he's 4. So that's plus 2. So right there. And then the next one's going to be plus 8. 1, 2, 3, 4, 5, 6, 7, 8. Boy, it's really kind of hard to tell. Oh, come on, pen. And then the next one's going to be plus 16. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 16. Let's just say it's about right there. Okay, so what you should notice happening, and really I know they look so similar, especially how I didn't even make the curve very good. What you notice is that the tortoise was ahead to begin with. It looks like they were exactly the same at 2 seconds. And then what happened is after that, below, so it looks like, okay, so above, the same. This was below, this is, okay, how did that happen? So the same again. And then it was above and then above. So it looked like it passed it and then it came back and passed it again. So then it becomes higher up here. So the rates of change are really changing here quite a bit. In the beginning, the hair was going faster. And then right about here, they were going about the same speed. And then the blue one started to catch up back again. So that means the tortoise was going faster from here to here until they're the same speed, these two different places. So imagine what I'm talking about. So it passes it, and then it passes back again, and then it looks like from there on, the blue one's going to always be higher. Exponentials go up faster than quadratics do because they're multiply and not adding. All right, so that I kind of really just answered all of these questions right here. So let's talk about rates of change. And this is another way of writing rates of change. If t is the amount of seconds, the amount of time, so from 0 to 2, that's really what's asking you. What was the rate of change from 0 to 2? So I'm going to go back and I'm going to do the same thing for the hair and the torso. I'm just splitting this in half. So let's look at the hair from 0 to 2. From 0 to 2, it increases by 4 after 2 seconds. So it's increasing by 4 in 2 seconds. So that would be a rate of change of 2. So we're trying to find what was the interval. So what was, use the properties to compare the speeds of the tortoise and the hare for the following time intervals. So that one was going by 2, or up 4 for every right 2. The tortoise from 0 to 2 was going, it looks like it went up 3 in 2 seconds. Up 3 in 2 seconds. So clearly the hare was going faster in the first 2 seconds. And then what about from 2 to 4? From 2 to 4, it goes up 12 in 2 seconds. Up 12 in 2 seconds. Whereas the hare from 2 to 4 goes also up 12 in 2 seconds. So it looks like they're going exactly the same during that time interval. And then the last one, from 4 to infinity, we can see that, well, let's just go from 4 to 6. From 16 to 36, that's an increase of 20 over 2 seconds. and the tortoise is going to increase from 16 to 64. So that would be 4 to get to 20 plus 40 more to get to 60. So that's 44 plus 4 more again makes 48. So that's increasing by 48 in 2 seconds. So clearly the tortoise is going faster from 4 to infinity, as I had mentioned when I was talking about the graph. All right, so let's get to the homework, and it's very similar. You can see, once again, now we're talking about a linear piece versus what looks to be either a quadratic or an exponential. We're not quite sure until we really look at the data. So we're comparing linear, quadratic, and exponential functions. The graph on the right shows time versus distance for 2 graphing cars. Which car had the cruise control on? The cruise control on was definitely A. How do I know that? I know that because I'm not going to write this. I know it because it went at a constant rate. It's a linear equation. It's cruising, you know, its distance traveled is increasing at a constant rate because it's going at a very constant speed. It's staying the same speed, which means it's going up at the same rate. Which car is accelerating? That would definitely be B. And I would say it probably starts accelerating about right here. I mean, it's accelerating a little bit here, but then it starts accelerating quite a bit. And then it accelerates at almost like a constant rate. All right, so that was quite easy. So basically in the beginning, A had a greater rate of change until about right here. You can see A goes up a little bit faster from here to here, but then from here to here, B goes up faster, and then they're exactly the same, and then B is going up faster for the rest of till infinity, I guess. All right, thanks again for watching. Please give it a like if it helped you learn something, and follow me if you haven't done so already, or just tell people and have them follow me. All right, thanks again for watching.